Our reality is split in two. The rules for the smallest particles are completely different from the laws that guide entire galaxies. This fundamental schism is the frontier between quantum reality and cosmic scale, and bridging it is the greatest unsolved mystery in physics today. By the end of this journey, you will understand not just the science, but what this unification means for our very place in the cosmos. We will venture from the bizarre heart of a black hole, where all known laws break down, to the first instant of the Big Bang, when the entire universe was smaller than an atom. How can a world built on fuzzy probabilities give rise to the solid cosmos we see? What does it mean if time itself is not fundamental? The search for answers is reshaping our conception of existence itself. What part of this cosmic puzzle feels most mysterious to you? This fundamental strangeness is not a bug in the system, it is the system itself. To grasp the frontier, we must first fully appreciate the bizarre rules of the quantum realm, a place where logic as we know it dissolves. Think of an electron. In our world, you are either here or there, but for that electron, reality is not so definite. It exists as a shimmering cloud of probability, a state called superposition, where it can literally be in multiple places or spin in multiple directions, all at the same exact time. It is only when we make a measurement, that this cloud collapses into a single, solid fact. This is the first cornerstone of quantum weirdness. Then there is entanglement, a connection so profound it baffled even Albert Einstein, who famously called it spooky action at a distance. When two particles become entangled, they are linked in a way that transcends space. Change the state of one, no matter if it is across the room or across the galaxy, and its partner instantly reflects that change. This is not a signal traveling. It is a deeper, instantaneous correlation that suggests the universe at its core is fundamentally interconnected in ways we cannot yet picture. These principles of superposition and entanglement were forged in the intellectual fires of the early 20th century by pioneers like Niels Bohr and Erwin Schrödinger. Their work gave us quantum mechanics, a mathematical framework of stunning precision for predicting the behavior of atoms and particles. Yet the theory offers no comforting story of what is actually happening. It simply gives us the probabilities, the odds of finding a particle here or there. The most iconic demonstration of this is the double slit experiment. Fire a single particle, like an electron, at a barrier with two narrow slits. You would expect it to go through one slit or the other and hit a detector behind the barrier, making a single mark. But that is not what happens. Over time, the electron builds up an interference pattern, a series of light and dark bands, as if it passed through both slits at once like a wave interfering with itself. It behaves as both a particle and a wave, a duality that depends entirely on whether we are watching. This is the heart of the quantum mystery. How does a universe built on such fuzzy, probabilistic foundations, operating on scales a billion times smaller than a meter, give rise to the rock-solid, definite reality of our everyday world? The answer, it seems, lies in the contrasting domain that governs the cosmos itself. While the quantum realm thrives on probability, the cosmos presents a vision of majestic order. This cosmic framework is governed by Albert Einstein's theory of general relativity, a masterpiece of human thought that describes the universe at its grandest scales. Here, reality is not a collection of fuzzy probabilities but a smooth, continuous, and beautifully predictable fabric. Envision space and time not as separate entities, but as a single, dynamic material called space-time. Planets, stars, and galaxies do not simply move through this fabric, they mold it. A massive object like our Sun creates a deep well in this space-time fabric, and Earth travels along the curved contours of that well, which we experience as the force of gravity. It is not a mysterious pull, but the natural motion of an object following the shape of the universe itself. This elegant theory has passed every test with astonishing precision. It explains the subtle wobble in Mercury's orbit that Newton's gravity could not. It predicts how the path of starlight will bend as it passes a massive galaxy, a phenomenon called gravitational lensing that allows us to see distant cosmic objects magnified and warped like a natural telescope. On the scale of light years, where gravity is the undisputed architect, general relativity paints a picture of a deterministic reality. If you know the mass and energy of everything in the universe, the theory suggests you could, in principle, predict its entire future. This is the cosmic order, a stark contrast to the quantum world's inherent uncertainty. Yet for all its power, this beautiful framework has a breaking point. It fails utterly when confronted with the extremes of nature, places where immense gravity is squeezed into an unimaginably tiny volume. At the very heart of a black hole, according to general relativity, all matter is crushed into a point of infinite density called a singularity. Here, the equations of relativity produce nonsensical answers, numbers that become infinite, signaling that our understanding of physics has completely broken down. Similarly, if we rewind the cosmic clock to the very first instant of the Big Bang, the entire observable universe was compressed into a space smaller than a subatomic particle. In these domains, the colossal force of gravity meets the bizarre rules of the quantum world. General relativity cannot describe it, and quantum mechanics was not built for it. Their violent clash is not a minor theoretical dispute. It is a screaming signal that a deeper, unified truth is waiting to be found. To witness this frontier in its rawest form, we must confront the ultimate cosmic paradox, the black hole. A black hole is where our two descriptions of reality go to war. At its heart lies a singularity, a point where the equations of general relativity predict infinite density and a curvature of space-time so severe that the mathematics simply breaks. It is a place where the smooth, geometric fabric of the cosmos is shredded, and the concept of here and there loses all meaning. Yet, into this realm of ultimate gravity, we must now bring the quantum world. Quantum mechanics tells us that empty space is not truly empty, but a seething, bubbling foam of virtual particles flickering in and out of existence. At the very edge of a black hole, its event horizon, this quantum foam creates a profound paradox. Sometimes, a pair of these virtual particles will appear, and one will fall inward past the point of no return, while the other escapes into the universe. The particle that escapes carries away a tiny bit of energy, and to conserve energy, the black hole itself must lose a corresponding amount of mass. This is Hawking radiation, the brilliant insight from Stephen Hawking that showed black holes are not entirely black, but can slowly evaporate over cosmic timescales. Here was the first concrete collision, a quantum process having a direct, calculable effect on a gravitational giant. But this revelation created a deeper crisis, known as the information paradox. In quantum mechanics, information is never truly destroyed. It is merely scrambled. But if a black hole evaporates completely, what happens to all the quantum information about every star, planet, or book that ever fell in? Does it vanish, violating a core quantum rule, or is it somehow encoded in the Hawking radiation, a cosmic puzzle we cannot yet decipher? This paradox forces us to accept that our two theories are not just different, they are fundamentally incompatible at this frontier. The smooth space-time of a black hole described by Einstein cannot coexist with the violent quantum fluctuations that Hawking described. One of these pictures, or perhaps both, must be an approximation of a deeper truth. To resolve this, we need a framework where gravity itself is quantum in nature. This quest has led physicists to the most ambitious and elegant candidate for a theory of everything, a vision where the very threads of reality are woven from vibrating strings. If the black hole is where our theories clash, the Big Bang is where they were born from the same impossible source. The very origin of our universe presents the ultimate collision point, a moment when the entire cosmos existed on a scale where quantum rules were the only rules. Rewind time to the first fleeting instance after the initial event. The entire observable universe, everything we can see across billions of light years, was compressed into a space far smaller than a single atom. At that scale, the dominant force was not gravity as we know it, but the wild, probabilistic fluctuations of the quantum foam. In this seething primordial soup, the concepts of here and there, before and after, had no stable meaning. How could such a chaotic, fuzzy beginning give rise to the vast, structured cosmos we inhabit today? The leading answer is a theory called cosmic inflation, proposed by physicists like Alan Guth. It suggests that a peculiar quantum field, a kind of energy inherent to empty space itself, triggered a period of unimaginably rapid expansion. For a fraction of a second, the universe doubled in size over and over again, faster than the speed of light, stretching a microscopic seed into a macroscopic landscape. Crucially, during this violent growth spurt, the tiny quantum ripples and fluctuations in that field were stretched along with it. Those microscopic wrinkles in the fabric of reality became the gravitational seeds for everything to come. The denser spots in this stretched quantum tapestry eventually, over billions of years, collapsed under their own gravity to form the first galaxies, stars, and the vast cosmic web we observe. Think of it like blowing up a balloon with a faint, microscopic pattern drawn on its rubber. As the balloon inflates to an enormous size, that tiny pattern expands into a large, clear design across its entire surface. In this breathtaking vision, the grand architecture of the universe, the distribution of galaxies across the void, finds its origin in quantum randomness. The very large is quite literally imprinted with the signature of the very small. Yet for all its explanatory power, inflation still runs into a wall when we try to look at the exact moment of creation itself. Our equations point to a beginning, a singularity of infinite density and temperature, where both general relativity and quantum mechanics cease to provide sensible answers. It is the ultimate gap in our cosmic story. To understand the true origin, to peer into that first moment, we require a language that does not treat gravity and quantum behavior as separate things. This forces us to question the very mathematics we use to describe reality, pushing us toward frameworks that are as beautiful as they are strange. This paradox of the cat in the box is not just a quirky thought experiment. It is the stark face of the measurement problem, the deepest philosophical rift in all of physics. Why does the mere act of looking, of making a measurement, force a shimmering cloud of possibilities to collapse into a single, solid fact? In our everyday world, a tree falls in the forest whether anyone hears it or not. But in the quantum realm, it seems the tree exists in a superposition of both standing and fallen states until an observer arrives. This forces a profound question. Is reality fundamentally fuzzy, only becoming concrete when an intelligent mind interacts with it? The most famous answer for decades was the Copenhagen interpretation, championed by Niels Bohr. It takes a pragmatic, almost engineering approach. It says, do not ask what is happening between measurements. The mathematics gives us probabilities, and when we look, the wave function collapses into a definite outcome. It is a rule for calculation, not a description of an underlying reality. For many physicists, this works perfectly well in the lab, but it leaves the nature of that collapse utterly mysterious. What exactly qualifies as a measurement? Is it a photon hitting a detector, a scientist writing down a number, or something else entirely? In stark contrast stands the many worlds interpretation. It proposes a breathtakingly elegant yet staggering solution. There is no collapse at all. Every possible outcome of a quantum event actually occurs, but each one plays out in a newly branched parallel universe. In one branch of reality, Schrödinger's cat is alive. In another, it is dead. The universe continuously splits into a vast, ever-growing multiverse of possibilities, and we simply find ourselves in one thread of that infinite tapestry. This interpretation removes the special role of the observer, but at the cost of accepting an unfathomable proliferation of realities. Then there is the most provocative layer pondered by physicist Eugene Wigner. He asked if consciousness itself might be the trigger for collapse, that the universe requires a conscious observer to bring it into definite being. This idea pushes the measurement problem from physics into the realm of philosophy and mind, suggesting a cosmos that is not independent, but in some deep way participatory. While this view is a minority among scientists, it highlights how high the stakes are. This is not an academic debate. The measurement problem sits at the very interface between the quantum fog and the classical world we perceive. Its resolution is not optional. It is essential for any complete theory of quantum gravity. How can we describe the birth of the universe from a quantum state if we do not understand how definiteness emerges? How can we model the interior of a black hole where space and time break down if we do not know what reality truly is at its core? Every attempt to cross the frontier from string theory to loop quantum gravity must eventually confront this chasm. The journey to unify reality may well depend on answering a seemingly simple question. What happens when we look? The measurement problem is not a dead end. It is a signpost pointing toward a grander unification. For decades, the most brilliant minds in physics have pursued a single, coherent rulebook for reality, a framework known as quantum gravity. This is not merely an academic exercise, it is the essential next step for our species' understanding of the cosmos. Without it, our picture of existence remains fractured, with one set of laws for the infinitesimally small and another for the astronomically large. The goal is breathtakingly ambitious: to describe the force of gravity using the same quantum principles that govern the other three fundamental forces. Think of it as trying to write a universal language that can narrate the story of a vibrating electron and the orbit of a planet with equal clarity. Two towering ideas dominate this quest, each offering a radically different vision of the universe's deepest fabric. The first is string theory. It proposes a fundamental shift in what we consider the most basic building block of nature. Forget point-like particles. Imagine instead that every fundamental entity, from quarks to photons, is actually an unimaginably tiny, vibrating loop or strand of energy, a string. Just as a single violin string can produce different notes depending on how it vibrates, these cosmic strings vibrate in distinct harmonics. One resonant pattern might correspond to an electron, another to a quark, and crucially, one specific vibration would correspond to the graviton, the hypothetical quantum particle of gravity. In this elegant symphony, all forces and matter are unified as different manifestations of these vibrating strings. String theory mathematically requires extra dimensions of space, curled up at scales so small we never perceive them, offering a rich, multidimensional landscape for reality. The second major approach is loop quantum gravity. It takes a different starting point, asking not what matter is made of, but what space itself is made of. In this view, the smooth, continuous space-time of Einstein's relativity is an illusion that emerges from something more fundamental. Space is not infinitely divisible. Instead, it is woven from a network of incredibly tiny, discrete loops, like a cosmic fabric with a finite, granular weave. These loops and their intersections define the quantum geometry of the universe, with the smallest possible size for any volume or area. This granularity provides a natural escape from the dreaded singularities of black holes and the Big Bang, because you simply cannot compress matter and energy into an infinitely small point. There is a limit, a smallest possible stitch in the fabric of reality. Both theories are monuments of human imagination and mathematical beauty, yet they exist in a challenging realm. They make profound predictions, but those predictions often concern energies and scales so extreme that we currently have no way to directly test them with experiments. We are like architects who have drafted blueprints for a new kind of universe, but we lack the tools to build even a small model. This does not make the pursuit pointless, far from it. The search itself is reshaping our conception of what is possible, forcing us to ask deeper questions about time, causality, and the very nature of existence. It is a reminder that the frontier is not just out in the cosmos, it is in the fundamental architecture of everything, waiting for a new generation of thinkers to find a crack in the puzzle and let the light in. The search for quantum gravity often feels like a pursuit of shadows, a theory in search of a test. How can we verify ideas about the universe's smallest stitches when our most powerful tools are still astronomically crude? The answer lies not in building a bigger machine here on Earth, but in turning the cosmos itself into our laboratory. Scientists are now designing ingenious experiments that use the universe as a precision instrument, listening for whispers from the frontier in the silent depths of space. One of the most promising avenues is the hunt for primordial gravitational waves. These are not the ripples from colliding black holes we have already detected, but something far more ancient and subtle. They are echoes from the universe's first violent moments, potentially imprinted with the signature of quantum gravity itself. As space-time underwent its rapid inflationary expansion, the wild quantum fluctuations in the gravitational field would have been stretched into literal waves in the fabric of reality. Detecting these faint tremors would be like finding the fossilized heartbeat of the Big Bang. Future observatories like the planned Laser Interferometer Space Antenna, a fleet of 3 spacecraft flying in a perfect triangle millions of kilometers apart, will listen for these whispers with unprecedented sensitivity. It is a direct attempt to hear the quantum noise of creation amplified to a cosmic scale. We can also look for clues in the oldest light in the universe, the cosmic microwave background. This faint afterglow bathing all of space is a snapshot of the cosmos when it was just 380,000 years old. Embedded within its subtle temperature, variations could be patterns, like faint brushstrokes on a vast canvas, that reveal the nature of those initial quantum seeds. Did they follow the statistics predicted by string theory? Do they show hints of the granular structure of space proposed by loop quantum gravity? Scrutinizing this cosmic fingerprint is like performing forensics on the moment reality transitioned from the quantum fog to the classical cosmos. Closer to home, though no less extreme, are the dense corpses of dead stars. Neutron stars pack more mass than our Sun into a sphere the size of a city, creating gravitational fields so intense they verge on the quantum regime. By precisely measuring how these stars wobble, pulse, and interact, we can test how matter and gravity behave under conditions that push our theories to their breaking point. Even tabletop experiments with clouds of atoms cooled to near absolute zero are creating exotic states of matter that mimic conditions in the early universe or near black holes, offering a controlled, miniature window into quantum gravitational effects. While a definitive, direct observation remains on the horizon, each of these efforts represents a crucial step. They transform the quest from pure mathematical speculation into a tangible line of empirical inquiry. This experimental hustle does more than test theories, it reframes a fundamental question. If information is truly never lost, as quantum mechanics insists, then the universe operates like a perfect, if immensely complex, ledger. Every interaction, from the decay of a particle to the merger of galaxies, is an entry in this cosmic book. The search for quantum gravity, then, is ultimately a search for the language in which this universal ledger is written. Are its pages woven from vibrating strings or from a network of quantum loops? The experiments now underway are our first attempts to decipher a single, profound sentence from a text that describes everything. The universe might be a projection, a cosmic illusion of depth. This is the staggering implication of the holographic principle, an idea born from the fiery paradox of black holes. Physicists Gerard T. Hooft and Leonard Susskind proposed it as a radical solution to the information paradox. They asked, what if all the information that falls into a black hole is not lost inside, but is instead perfectly encoded, pixel by pixel, on its two-dimensional event horizon, the surface of no return? The three-dimensional interior, with all its complexity, would then be like a hologram projected from the data on that flat, bounding surface. Think of a credit card hologram, the kind that shows a three-dimensional eagle that seems to shift and move. All the information needed to create that illusion of depth is stored on the flat, shiny sticker. The holographic principle suggests reality itself might work the same way. Your experience of living in a three-dimensional world, of moving through space, could be a magnificent projection from a vast, distant, two-dimensional screen. This idea does more than solve a black hole puzzle. It redefines the nature of space-time. If true, then dimensions themselves might not be fundamental. The solidity and volume we perceive could be emergent properties, illusions that arise from a vast network of quantum information exchanges happening on a boundary we cannot see. This flips our intuition about locality completely. An event happening here, in this room, might in some fundamental sense be described by information stored on a cosmic boundary at the edge of the observable universe. It suggests a universe that is deeply interconnected in a way that makes quantum entanglement seem like a simple hint of a much grander, woven tapestry. The principle offers a tantalizing path toward unifying gravity with quantum mechanics because it simplifies the problem dramatically. Describing a three-dimensional volume of space with gravity is immensely complex, but describing the physics on its two-dimensional boundary might be far simpler, using quantum rules we already understand. In this view, gravity and the very geometry of space are not primary forces, but side effects, emergent phenomena that arise from the way quantum information is processed and displayed on the cosmic screen. We are left with a profound question. If our reality is a hologram, what or who is holding the projector? The holographic principle hints at a universe built from information, but what is the physical thread that weaves that information into the geometry we experience? The answer may lie in the strangest phenomenon of all, quantum entanglement. Recent theoretical breakthroughs are pointing toward a startling possibility. The very fabric of space-time, the stage upon which the cosmos unfolds, may be woven from these spooky quantum links. To understand this, we need to revisit entanglement with new eyes. When two particles become entangled, their fates are linked in a way that transcends ordinary distance. Measure one, and you instantly know the state of its partner, no matter if it is across the lab or across a galaxy. Einstein famously dismissed this as spooky action at a distance, an uncomfortable ghost in the machine of his orderly universe. But what if this spookiness is not a bug, but the fundamental feature? Researchers like Juan Maldacena have explored models where space-time geometry itself emerges from entanglement. Imagine a simple, empty universe with a boundary, like the surface of a sphere. On that boundary, you have a vast network of quantum particles that are intricately entangled with one another. The theory suggests that the interior, three-dimensional volume of that space is not a separate place, but a geometric projection of those boundary entanglements. The more entangled the particles on the boundary are, the more connected or shorter the pathways through the interior become. This leads to an astonishing idea known as ER equals EPR. It proposes a deep equivalence between two concepts that seemed utterly unrelated. EPR stands for the Einstein-Podolsky-Rosen paradox, the paper that first highlighted the weirdness of entanglement. ER stands for Einstein-Rosen bridges, the formal name for wormholes, theoretical tunnels through space-time. The equation suggests that two entangled particles might be connected by a microscopic wormhole, a bridge in the geometry of space. This is not a tunnel you could travel through, but it represents a fundamental connectivity. In this view, what we perceive as closeness in space, the fact that you are closer to your chair than to a star, might fundamentally arise from the density and strength of the quantum entanglement links between things. The vast cosmic distance between two stars, then, could be seen as a manifestation of a very weak or diluted entanglement between them. This transforms entanglement from a curious laboratory quirk into a potential cosmic architect. It provides a tangible bridge between the world of quantum information and the curved geometry of general relativity. If space itself is a tapestry of quantum links, then the force of gravity and the very structure of the cosmos may be emergent phenomena, side effects of a deeper, information-based reality. This prompts a profound shift in perspective, encouraging us to look at other cosmic puzzles not as problems of gravity alone, but as potential expressions of quantum entanglement on a universal scale. The universe is not just expanding, it is accelerating, driven by a mysterious pressure we call dark energy. This invisible force, making up about 70% of the cosmos, presents a profound and quiet frontier where quantum reality meets the cosmic scale. To understand it, we must reimagine the void. Empty space, according to quantum field theory, is not empty at all. It is a dynamic sea, a seething foam where pairs of virtual particles and antiparticles constantly flicker into existence, borrowing energy from the vacuum for a fleeting moment before annihilating each other. This quantum jitter is not just theoretical, it has real, measurable effects in the lab, like the Casimir force, where two metal plates placed extremely close together feel a subtle push from the particles popping into being in the gap between them. This vacuum energy should, in principle, contribute to dark energy, acting as a constant pressure pushing space itself apart. But here we encounter one of the most staggering failures of prediction in all of science. When physicists calculate the expected energy density of this quantum vacuum, the number they get is unimaginably large, about 120 orders of magnitude larger than the amount of dark energy we actually observe. That is not a small error. It is a number so colossal that writing out the difference would require more zeros than there are particles in the observable universe. This is the cosmological constant problem, and it is a screaming alarm that our understanding is profoundly incomplete. The quantum vacuum's energy, as we currently calculate it, should have ripped the cosmos apart in a fraction of a second after the Big Bang, or caused it to collapse instantly upon itself. Neither happened. Instead, we have a universe that expanded gently for billions of years before this subtle dark energy recently began to dominate. This discrepancy is not just a math error, it is a clue. It suggests that something is deeply wrong with how we are connecting the quantum world to gravity on cosmic scales. Perhaps the quantum vacuum energy does not gravitate the way ordinary matter and energy do. Maybe it is balanced by some unknown opposing principle, or more radically, our theory of quantum fields, which works perfectly in the flat, static space-time of a laboratory, breaks down when applied to the dynamic, curved geometry of the entire expanding universe. Solving this puzzle may require a revolutionary insight that fundamentally alters either quantum field theory in the context of gravity, or our conception of gravity itself on the largest scales. Dark energy reminds us that the frontier is not only found in the violent hearts of black holes or the first instant of time. It is woven into the very fabric of the nothingness between the stars, in the silent hum of the quantum vacuum, waiting for a new physics to explain why the cosmos is gently, yet relentlessly pushing itself apart. Dark energy reveals a gap in our equations, but another frontier lies within the observer themselves. This brings us to the most speculative and profound layer of the mystery, the potential role of consciousness. While mainstream physics focuses on mathematical formalism, a compelling interpretation proposed by figures like John von Neumann and Eugene Wigner places the mind at the very center of reality. It suggests the collapse of the quantum wave function. The moment probability snaps into definite fact is triggered by the conscious observation of a sentient being. In this view, the universe remains in a shimmering state of potential until a conscious mind interacts with it, essentially bringing reality into concrete existence through the act of perception. This idea is not a testable scientific theory in the traditional sense, and it remains a distinct minority view among physicists, who generally seek explanations that do not rely on such a special role for consciousness. Yet, it sparks an undeniable and deep line of questioning that forces us to confront the relationship between the observer and the cosmos. It asks whether the emergence of the solid, classical world we experience is somehow intrinsically tied to the emergence of consciousness itself. Are we merely passive witnesses to a universe unfolding on its own, or are we, in some fundamental way, participants in its creation? This speculation has led some researchers to explore models where consciousness itself might arise from specific, delicate quantum processes within the brain, such as orchestrated reductions in microtubules, the tiny scaffolding within our neurons. These proposals are highly controversial and face significant scientific hurdles, but they represent a bold attempt to build a bridge between the physics of the very small and the phenomenon of subjective experience. Engaging with these ideas, even speculatively, highlights the profoundly interdisciplinary nature of this ultimate frontier. The quest to unify reality cannot be confined to physics alone. It spills over into neuroscience, philosophy, and the deep mystery of our own awareness. It challenges us to consider a staggering possibility that to fully understand the cosmos, we may first need to understand the nature of the conscious observer that is trying to comprehend it. This philosophical journey, however, is now leading to something remarkably tangible: the dawn of technologies that will allow us to touch the quantum world directly. The philosophical questions of consciousness lead directly to a tangible, world-changing endeavor. We are no longer just pondering the quantum realm, we are beginning to build with it. The drive to understand this frontier is fueling a technological revolution, most powerfully embodied in the quest for quantum computing. This is not a distant dream, but an active engineering challenge that takes the bizarre principles of superposition and entanglement and attempts to harness them for practical calculation. At its heart is a new kind of bit, the quantum bit or qubit. Unlike a classical computer bit, which is definitively a 1 or a 0, a qubit can exist in a superposition of both states simultaneously. Think of it not as a switch, but as a spinning coin caught in a state that is both heads and tails at once. By entangling multiple qubits together, a quantum computer can, in a sense, explore a staggering number of possible solutions to a problem all at the same time. This parallelism offers the potential to crack problems that would take even our most powerful supercomputers longer than the age of the universe to solve. The implications are profound. It could allow us to design new materials molecule by molecule, simulate complex chemical reactions to discover life-saving drugs, or optimize global logistics networks in ways we can barely conceive. Perhaps most fittingly, a mature quantum computer could be used to simulate other quantum systems with perfect fidelity, letting us model the behavior of exotic materials or even aspects of the early universe itself, turning the cosmos into a solvable equation. Yet, to make this work, engineers face a challenge that echoes our deepest cosmic mystery: they must protect these delicate quantum states from the very thing that makes our everyday world solid, the environment. Any interaction with the outside world, a stray photon, a vibration, even a cosmic ray, can cause the qubits to lose their fragile superposition and collapse into definite ones and zeros. This process is called decoherence, and fighting it is the central battle in building a practical quantum computer. To win, scientists create incredible environments of extreme cold, near absolute zero, and exquisite isolation, building shields against the classical world to preserve quantum magic. In this struggle, the quantum computer becomes more than a tool. It becomes a living laboratory. The fight against decoherence is a direct, hands-on study of the quantum to classical transition. Every microsecond of coherence preserved, every error corrected, provides tangible data on how a probabilistic quantum state gives way to a definite classical reality. It is as if we are running a continuous experiment on the measurement problem itself, gathering clues about how the universe makes the jump from fuzzy potential to solid fact. By trying to engineer and control the quantum realm, we are actively probing the very boundary that defines our reality, turning abstract theory into working hardware that may one day help us read the universe's deepest code. While we build quantum machines to master the small, our gaze is also stretching across the cosmos with tools of breathtaking power. The drive to map the universe's grand architecture is birthing a new generation of observatories, instruments so sensitive they feel less like telescopes and more like time machines. Consider the James Webb Space Telescope. Orbiting 1,000,000 miles from Earth, its golden mirrors are not just collecting light, they are gathering ancient stories. By peering into infrared wavelengths, it sees through cosmic dust to capture the faint glow of the very first galaxies, systems that formed when the universe was a mere infant. Each image is a direct look back across more than 13 billion years, allowing us to witness the cosmic dawn, the moment when the primordial fog cleared and the first stars ignited. This is not just astronomy, it is archaeology on a universal scale, examining the infant universe to understand how the mature cosmos came to be. On a mountaintop in Chile, the Vera Sea, Rubin Observatory prepares for a different kind of survey. Its gigantic camera will scan the entire southern sky every few nights, creating a monumental, time-lapse movie of the cosmos. It will chart billions of galaxies, track millions of asteroids, and watch for fleeting, explosive events. Its primary mission, however, is to map the invisible. By precisely measuring how the light from distant galaxies is warped as it travels to us, Rubin will chart the distribution of dark matter, the mysterious gravitational scaffold that holds the universe together. These tools test Einstein's general relativity with a precision he could never have dreamed of, searching for any subtle crack in the theory's predictions. Does gravity behave exactly the same across cosmic voids as it does within a galaxy cluster? Any tiny deviation could be the whisper of new physics, a hint that quantum effects or modifications to gravity are at play on the largest scales. Beyond light, we are learning to listen to the universe in new ways. Ambitious projects aim to detect the faintest tremors in reality itself, primordial gravitational waves. These are not the ripples from black hole mergers we have already heard, but echoes from the universe's first violent fraction of a second. Capturing this signal would be like putting a stethoscope to the moment of cosmic inflation, hearing the quantum jitters of space-time stretched to a cosmic roar. Similarly, experiments hunt for relic neutrinos, ghostly particles that have streamed freely since the first second after the Big Bang. Catching them would give us a direct sample of the universe in its fiery infancy, a snapshot from an era when all forces were likely one. This technological arms race, spanning from quantum labs to mountain peaks and orbital outposts, creates a powerful synergy. The same advanced materials and sensor technologies developed to shield qubits from decoherence can be adapted to make cosmological detectors more sensitive. Insights from quantum information theory may suggest new ways to analyze the colossal datasets from telescopes like Rubin. In turn, the extreme conditions observed in the cosmos provide the ultimate testing ground for theories born in the quantum realm. Each new instrument, whether it probes the fabric of space or the behavior of a single atom, is a thread being woven into a single, grand investigation, proving that the frontier between the quantum and the cosmic is not a barrier but a bridge. Our technological probes into the quantum and the cosmic are forcing a profound philosophical reckoning. We are not just mapping the universe, we are questioning its very nature. The frontier compels us to ask what is real, the classical worldview inherited from Newton and solidified in our daily experience, presents reality as a stage. Objects exist with definite properties and time flows uniformly, with an observer merely watching the play unfold from the seats. But the quantum cosmic synthesis shatters this comforting image. In its place, we are offered a startling possibility that the solidity of objects and the continuous flow of time are not fundamental. They may be emergent properties, collective illusions that arise from the ceaseless hum of underlying quantum processes. Think of a movie. On the screen, you see a fluid, continuous narrative of people moving through a world. But if you examine the film strip itself, you find it is not a continuous flow at all. It is a series of static, individual frames. The illusion of smooth motion emerges from the rapid succession of these still images. Some interpretations of quantum mechanics and frameworks like loop quantum gravity suggest our experience of time and solidity might be similar, a high-level perception arising from a deeper, discrete quantum substrate. In loop quantum gravity, for instance, space itself is not smooth but granular, composed of tiny, indivisible loops. The passage of time might emerge from the changing relationships between these quantum units, not from a universal river flowing on its own. This directly challenges the idea of an objective, observer-independent universe. If properties only become definite through interaction, as quantum mechanics suggests, then reality is inherently relational. An electron does not have a definite position until it interacts with something else, whether that is a detector or another particle. Its reality is defined by its relationships within a network. This moves us toward a participatory view, where the universe is not a pre-written script but a dynamic tapestry being woven through an endless web of interactions. Philosopher of science Carlo Rovelli explores this deeply, arguing that physics is less about cataloging what is and more about understanding the structure of these interactions. Existence itself may be constituted by this web. To know a thing is not to see it in isolation, but to understand its place and its effects within the cosmic network. This perspective can feel disorienting, stripping away the absolute ground beneath our feet. Yet, it is also profoundly liberating. It suggests we are not passive spectators in a cold, deterministic machine, but active participants in an unfolding, interconnected reality. Our observations, our measurements, are not mere recordings, they are stitches in the fabric. Engaging with these questions is not a philosophical diversion from hard science, it is the necessary next step. As we push toward a theory of quantum gravity, we are not just seeking new equations, we are seeking a new metaphysics, a new story about what it means to be and to know. This journey inevitably brings us to the final, humbling frontier, the limits of our own capacity to understand. Perhaps the most expansive consequence of this search is the multiverse hypothesis. It suggests our cosmos is not alone, but merely one bubble in a frothing, infinite sea of universes. This idea emerges naturally from two powerful strands of thought we have already explored. From cosmology, the theory of eternal inflation paints a picture where the rapid expansion of space never truly stops overall, but but instead, in different regions, it slows down to form isolated pocket universes, each with its own Big Bang and potentially its own unique set of physical laws and constants. From quantum mechanics, the many worlds interpretation takes every quantum possibility and gives it its own full-fledged reality, constantly branching the whole of existence into an ever-growing tree of parallel timelines. In both visions, our observable universe becomes a single thread in a tapestry of realities beyond any conceivable horizon. This framework offers a provocative answer to one of the deepest mysteries, the apparent fine-tuning of our universe for life. The fundamental constants of nature, like the strength of gravity or the mass of an electron, seem exquisitely balanced. If they were even slightly different, stars would not form, atoms would not hold together, and life as we know it would be impossible. The multiverse provides a staggering context for this. If there are an infinite number of universes, each with randomly different constants, then it is no longer a miracle that one exists with the right recipe for us. We simply find ourselves in the one where conditions allowed observers to arise. Yet this very explanatory power leads to a profound philosophical challenge. If these other universes are permanently beyond our observational reach, separated by unimaginable distances or existing in separate branches of reality, can the multiverse truly be considered a scientific theory? It pushes against the traditional definition of science, which relies on testable predictions and falsifiable evidence. Some argue it moves into the realm of metaphysics, a compelling story about reality that may forever lie outside empirical verification. Others counter that it is a natural, almost inevitable prediction of our best current theories of quantum gravity and inflation, and that indirect evidence, like specific patterns in the cosmic microwave background, could one day support it. Regardless of its scientific status, the multiverse stretches the frontier of our imagination to its absolute limit. It suggests the ultimate laws of physics may not describe a single universe, but a meta-reality, a vast landscape of possibilities where our entire cosmic story is just one quantum fluctuation given form. The multiverse stretches our imagination, but a more intimate puzzle lies within our own perception of the moment. The relentless tick of the clock, the feeling of a past flowing into a future, this sensation of time is so fundamental to our experience that we rarely question its reality. Yet at the frontier, physicists confront a deep and unsettling mystery known as the problem of time. In our two great rulebooks for reality, time plays two completely different roles, and reconciling them is one of the most difficult challenges in all of science. In Einstein's general relativity, time is not a universal metronome. It is a dynamic, flexible dimension woven together with space into a single fabric. Massive objects like stars and planets don't just warp space, they warp time itself. A clock ticks slower in a strong gravitational field than it does out in the empty void. Time is relative, it bends and stretches and is deeply entangled with the geometry of the cosmos. But in the standard textbook version of quantum mechanics, time is treated very differently. It is a fixed, external stage on which the quantum drama plays out. The equations tell us how a quantum state evolves in time, but they do not explain what time itself is. It is simply a parameter we plug into the math, an absolute background against which probabilities dance. This creates a profound conflict. How can we build a single theory of quantum gravity when one theory says time is a malleable part of the dynamic universe, and the other treats it as an immutable given? The search for a solution has led to a radical possibility that at the most fundamental level, time might not exist at all. This idea emerges from equations like the Wheeler-DeWitt equation in quantum cosmology, which attempts to describe the entire universe as a single quantum object. Strikingly, this equation lacks the variable for time. It describes a static, timeless wave function of the universe, a single, frozen quantum possibility. If this is the fundamental description of reality, then the flow of time we feel so deeply must be an illusion that emerges from something else. So where does our experience of past, present, and future come from? The leading clues point to two concepts we have already met: entropy and quantum decoherence. Entropy, a measure of disorder, always increases in our universe, giving us a clear arrow of time from a more ordered past to a more disordered future. The breaking of an egg, the melting of ice, the diffusion of scent in a room, these are all processes where we can clearly tell which way time is flowing. This increasing disorder may be the engine that creates our perception of a flowing time from a timeless foundation. Similarly, the process of decoherence, where quantum systems lose their fuzzy superpositions by interacting with their environment, appears to happen in one direction, creating a record of the past in the present. Every measurement, every interaction leaves a mark that wasn't there before, building up the consistent history we remember. This suggests that the river of time is not fundamental, but more like the current in a river, emerging from the collective motion of countless water molecules. Our conscious experience of duration and change could be a story our brains tell us, a narrative constructed from the ceaseless processing of quantum information in a universe that is, at its heart, a vast network of relationships. Reconciling these two views of time is not just philosophical, it is essential for understanding the very first moment of the universe. What were the initial conditions if there was no before? What set the arrow of time in motion? The answers may lie in seeing time not as a primary substance, but as something constructed from the same quantum threads that weave the fabric of space, a final turn in our journey back to the holographic principle and the deep, spooky connections of entanglement. The smooth fabric of space-time may be a magnificent illusion, a collective dream of the quantum world. This is the radical promise of emergent spacetime theories, which propose that the four-dimensional continuum we inhabit is not a fundamental stage, but a grand structure that arises from something simpler and more primitive. Think of a bustling city seen from an airplane window. From that height, you see a continuous, organized landscape of streets and buildings. But that city is not a fundamental entity. It emerges from the countless individual actions of people, cars, and systems working together. Emergent spacetime theories suggest our universe works the same way. The geometry of space and the flow of time could be high-level properties that bubble up from a vast, underlying network of quantum connections. The fundamental ingredients might not be tiny strings or loops, but quantum bits of information, simple units that can be in a superposition of states, intricately entangled with one another. This idea draws deep inspiration from the field of condensed matter physics, which studies how the collective behavior of simple parts gives rise to entirely new phenomena. Consider a simple magnet. A single iron atom has a tiny magnetic field, but it is not a magnet itself. Only when trillions of these atoms align their spins in concert does the familiar property of magnetism emerge, a property that does not exist for any one atom alone. In a similar way, theorists propose that if you have a vast, cold network of entangled quantum bits, their collective behavior and correlations could, on a large scale, give rise to properties that look exactly like geometry, distance, and even gravity. The smooth curvature of space described by Einstein could be a kind of statistical average, a story told by the quantum crowd. This approach flips the traditional quest for quantum gravity on its head. For decades, physicists have tried to quantize gravity to take Einstein's smooth geometric theory and chop it into discrete quantum pieces. Emergent spacetime suggests we might be going about it backwards. Perhaps we should not try to quantize gravity at all. Instead, we should start with the known rules of quantum mechanics and information, and ask how, under the right conditions, something that looks like gravity and geometry naturally crystallizes out. It is a bottom-up construction of reality from its most basic informational parts. This perspective offers a profoundly new way to view the most violent ruptures in our cosmos. If space-time is an emergent property, then a singularity like the heart of a black hole or the starting point of the Big Bang is not a place where physics ends. It is a place where the emergence breaks down, where the underlying quantum network becomes so scrambled or chaotic that the familiar concepts of here and now simply lose their meaning. There is no infinite density because the notion of density itself depends on a well-defined volume of space, and that volume ceases to exist as a coherent concept. The conflict dissolves because the smooth geometric description was only an approximation to begin with, one that fails under extreme conditions, much like the concept of liquid water fails when you look at individual jostling molecules. This is not a defeat for our understanding, but a potential liberation, pointing toward a deeper layer of reality where the most vexing paradoxes of the frontier might finally find their resolution. The universe's grand design was born from microscopic chaos. This is the breathtaking legacy of cosmic inflation, where the quantum realm directly wrote its signature across the heavens. During that unimaginably rapid expansion, the cosmos was not just stretching, it was amplifying the faintest whispers of the quantum world. The driving force behind this expansion is theorized to be a peculiar energy field, often called the inflaton field. Like all quantum fields, it was not perfectly smooth and calm. Due to the Heisenberg uncertainty principle, which states that on tiny scales there is a fundamental trade-off between knowing a quantity and knowing its change, this field was fizzing with tiny, random fluctuations. Think of it like the surface of a perfectly still pond at the quantum scale, not truly still, but shimmering with countless minuscule ripples appearing and disappearing. Then inflation hit, like suddenly stretching that pond to the size of an ocean. Those infinitesimal quantum ripples were stretched along with the fabric of space itself, frozen into the geometry of the universe as microscopic hills and valleys in the density of matter and energy. These became the gravitational seeds for everything, the slightly denser regions where a little more matter had pooled thanks to that initial quantum bump, had stronger gravity. Over billions of years, they pulled in more and more material, eventually collapsing to form the first galaxies, stars, and the vast cosmic web we see today. The evidence for this is etched into the oldest light we can see, the cosmic microwave background. That faint afterglow from when the universe first became transparent is not perfectly uniform. It is covered in a mottled pattern of tiny temperature differences, mere millionths of a degree. These spots are the direct, cooled-down imprint of those primordial density variations, a baby picture of the universe showing the quantum seeds already at work. We have mapped this pattern with satellites like Planck and WMAP, and it matches the predictions of inflation with stunning precision. This is one of the greatest triumphs of modern cosmology, a direct observational link between the probabilistic uncertainty of the quantum world and the large-scale structure of the entire cosmos. Yet a profound subtlety remains. How exactly did those quantum fluctuations, which exist in a fuzzy superposition of possibilities, become the definite classical density variations that we now observe as galaxies? This is the measurement problem playing out on the grandest possible stage. During inflation, the universe was essentially measuring itself. The rapid expansion acted to decohere the quantum possibilities, selecting one specific outcome from the many and imprinting it permanently onto the expanding fabric of space-time. The transition from quantum possibility to cosmic fact was not triggered by a human observer in a lab, but by the dynamic, gravitational evolution of the universe itself. Solving this puzzle is essential for a complete theory of cosmic genesis. It shows us that the order we see, the majestic swirl of galaxies, did not emerge from a prior, more perfect order. It emerged from fundamental randomness, a cosmic lottery at the quantum scale where every possible outcome was played, and our entire visible universe is the one ticket that was drawn. The frontier is not just about reconciling two sets of rules, but about understanding how something as definite as a galaxy could ever arise from a realm where nothing is ever truly definite at all. This paradox transforms a black hole from a cosmic vacuum cleaner into a philosophical furnace. At its core is a simple, devastating question. When an object falls into a black hole, every bit of information about it, the precise quantum state of every particle, seems to vanish behind an event horizon from which nothing, not even light, can return. Stephen Hawking's great insight added a cruel twist. He showed that black holes are not eternal. They slowly leak energy, emitting a faint thermal glow of radiation from their edges. Over timescales longer than the current age of the universe, a black hole can completely evaporate, leaving behind only this bath of warm radiation. The problem is that Hawking radiation, as he first calculated it, is purely thermal. It is random noise like the static from an old television, carrying no specific information about what fell in. If the black hole vanishes, the information about the book, the star, or the spaceship that crossed its horizon seems to be erased from reality forever. This violates a sacred principle of quantum mechanics, the law of unitarity, which states that information is never destroyed, only scrambled. You can burn a book, turning its orderly words into ash and smoke, but in principle, if you could track every particle of ash and wisp of gas, you could reconstruct the entire text. The black hole information paradox suggests the universe itself is burning the book in a way that leaves no trace at all. For decades, this stood as an impasse, a glaring sign that our understanding of gravity and quantum theory was incomplete. The resolution may be emerging from the holographic principle, the idea that all the information within a three-dimensional volume is encoded on its two-dimensional boundary. In this picture, the information about what falls into a black hole is not lost inside. It is smeared and stored on the event horizon itself, like data encoded on the surface of a DVD. As the black hole evaporates via Hawking radiation, this information is not carried away by individual particles of radiation, but in subtle, delicate correlations between them. Imagine the radiation is not a random hiss, but a complex symphony. Listening to a single note tells you nothing, but hearing the intricate relationships between all the notes reveals a hidden melody. The information is in the harmony, not the individual sounds. Recent breakthroughs in string theory, particularly the study of so-called quantum extremal surfaces or islands, suggest how this could work mathematically. These models show that as the black hole evaporates, the region of space that effectively holds the quantum information can extend outside the event horizon into the radiation field itself. The information never truly leaves the system. It just becomes distributed in a highly complex, non-local way. This ongoing saga is more than a technical puzzle. It forces us to refine our most basic ideas about what information is, how entropy works, and what constitutes a quantum state in the violently curved geometry of space-time. A black hole is not just an object in space, it is a theoretical crucible, heating our ideas until they either break or transform into something stronger. Resolving this paradox would not just tell us what happens to information, it would provide a monumental clue about how to weave the quantum world and the cosmic scale into a single, seamless tapestry of reality. The ultimate quantum system has no outside. Quantum cosmology forces us to apply the rules of the very small to the single, all-encompassing entity that is the universe itself. This creates a profound conceptual maze. In a laboratory, we define a quantum state by how it interacts with an external apparatus, a detector, an observer. But the universe, by definition, has nothing outside of it. There is no external clock to measure against, no outside environment to cause decoherence. How then do we describe its quantum state, or even define what a measurement would be? This is the arena of the Wheeler-DeWitt equation, a bold attempt to write a quantum description of the entire cosmos. Its mathematics are elegant, but its implications are dizzying. Most strikingly, the variable for time simply vanishes from the equation. It describes a static, timeless quantum possibility, a frozen wave function of everything. Our vivid experience of past, present, and future must then emerge from within this timeless description, like a story emerging from the arrangement of words on a page. This is the deep core of the problem of time. Furthermore, quantum mechanics deals in probabilities, the odds of this or that outcome, but we only have one universe to observe. How do we assign a probability to a single, unique event? What does it even mean to say the universe had a 90% chance of turning out one way and a 10% chance another, when we can only ever see the one result? To navigate this, physicists propose frameworks like the Hartle-Hawking no-boundary proposal. It imagines the origin of the universe not as a singular explosion from a point, but as a spontaneous quantum tunneling event. In this view, there is no sharp, initial boundary in time. Much like how the North Pole is a point on Earth but not an edge, you can travel north until you reach it and then keep going south. The universe simply begins, a smooth, self-contained geometry emerging from the quantum foam. Another compelling path comes from loop quantum cosmology, an application of loop quantum gravity to the early universe. It uses the idea of a granular, quantized space to avoid the singularity entirely. Instead of an infinitely dense starting point, the theory describes a cosmic bounce. Our expanding universe could have emerged from the collapse of a previous cosmic phase, a great rebound where gravity at the quantum scale becomes repulsive. In this model, the Big Bang is not the absolute beginning, but a transformative moment in an eternal cycle. These models are not just mathematical exercises, they are profound philosophical reorientations. They push the concepts of measurement and state reduction to a domain where there is no outside observer, only the universe observing itself through its own internal structure and evolution. Quantum cosmology represents the final, most extreme extrapolation of the frontier, asking us to consider that the totality of existence, with all its galaxies and voids, may itself be a single, vast quantum possibility that somehow selected its own definite history. Our universe seems perfectly tailored for life, but this fine-tuning may be an illusion of perspective. This is the core of the Anthropic Principle, a controversial idea that sits at the crossroads of physics and philosophy. It begins with a simple, almost tautological observation. The physical constants we measure, like the strength of gravity or the mass of an electron, must allow for our existence because we are here to measure them. We could never find ourselves in a universe where stars do not form, atoms do not hold together, or life is impossible. This is not an explanation for why the constants are what they are, but a statement about our unavoidable point of view, a selection effect. Think of a lottery winner. From their perspective, winning might seem like a miraculous one-in-a-billion event, but from the perspective of all the people who bought tickets, someone had to win. The winner's experience is real, but the odds are only meaningful when you consider the entire pool of participants. The Anthropic Principle suggests our universe might be that winning ticket, drawn from a vast cosmic lottery. This idea gains serious traction when combined with the Multiverse Hypothesis. If string theory or eternal inflation predicts a landscape of countless universes, each with randomly different physical laws, then it is no longer surprising that at least one of them, ours, has the right recipe for observers. We do not live in a special universe, we simply live in a habitable one because we could not perceive anything else. For some physicists, this feels like a philosophical retreat, an admission that we may never find a unique, fundamental reason for the numbers that govern our reality. It shifts the question from why are the constants this specific value, to to why does the multiverse allow for a range that includes a value compatible with life. Others argue it is a necessary and logical step when our theories naturally generate a landscape of possibilities. It forces a difficult dialogue about what we even mean by a scientific explanation. Is science only about finding deterministic causal mechanisms, or can it also encompass understanding the statistical framework within which our particular reality is embedded? Engaging with the Anthropic Principle adds a profound layer of meta-reflection to our entire exploration. It asks us to consider not just the laws of the universe, but the conditions required for there to be anyone around to contemplate those laws at all. This does not halt the search for deeper theory, but it reframes it, reminding us that any final picture of reality must account for the curious fact of our own presence within it. Our quest for a unified reality runs headlong into the very methods that built our modern world. Science, at its core, is a process of asking nature questions through controlled experiments. We isolate variables, make predictions, and test them against repeatable observations. This methodology has unlocked atoms, mapped genomes, and sent probes to other planets. Yet at the quantum cosmic frontier, this powerful toolset meets its operational limits. How do you conduct a repeatable, controlled experiment on the first instant of the Big Bang, an event that happened once, under conditions of energy and density that dwarf anything we can create? How do you directly observe the singularity at the heart of a black hole, a place from which no signal can ever escape? These are not just engineering challenges, they are fundamental barriers. The very regimes where our two great theories collide are, by their nature, inaccessible to traditional laboratory science. This forces a profound shift in how we seek knowledge. Without the possibility of direct experimentation, the search for quantum gravity leans heavily on other pillars of understanding. The primary guide becomes mathematical consistency. Does a proposed theory, like string theory or loop quantum gravity, hold together logically without internal contradictions? Does it naturally incorporate both quantum mechanics and general relativity in its framework? Scientists also rely on the power of the thought experiment, pushing logic to its extreme to reveal paradoxes, like the black hole information problem, that point toward deeper truths. And we turn to indirect cosmological evidence, scrutinizing the ancient light of the cosmic microwave background, or the ripples from colliding black holes for any faint imprint, any subtle deviation that might hint at the underlying physics of the extreme. This reliance raises deep philosophical questions about the nature of scientific proof. The influential philosopher Karl Popper argued that for a theory to be truly scientific, it must be falsifiable. It must make predictions that could, in principle, be proven wrong by observation. But what happens when a theory's most critical predictions concern energies a trillion times beyond our particle colliders, or phenomena hidden behind eternal event horizons? If a key aspect of a theory is permanently shielded from empirical test, does that render it unscientific? Or does the science of the frontier require us to evolve new criteria for validation, where mathematical elegance, explanatory breadth, and the resolution of deep theoretical paradoxes carry significant weight alongside traditional experiment? This is not an admission of defeat, but a call for profound intellectual humility and creativity. Acknowledging the limits of our current methodology is the first step toward transcending them. It pushes us to reconsider what constitutes evidence, to develop new kinds of cosmological probes, and to refine our philosophical understanding of how theory connects to reality. Perhaps the ultimate theory will be validated not by a single, spectacular experiment, but by a convergence of clues, a web of mathematical consistency, resolved paradoxes, and subtle, indirect signatures across multiple lines of inquiry. The frontier is testing not only our physics, but our very definition of how we know anything at all. The brain itself may be the most complex system we will ever study. Within its intricate networks, the mystery of consciousness presents a frontier that feels as deep and elusive as the quantum-cosmic divide. This has led a few bold thinkers to propose a direct bridge, suggesting that the phenomena of quantum mechanics might not just describe the universe, but could be actively at work within our own mind. The most famous of these proposals is the orchestrated objective reduction theory, which posits that delicate quantum processes inside structures called microtubules, found within our neurons, could be the seat of conscious awareness. In this view, consciousness arises from a specific kind of quantum computation happening at the cellular level, a symphony of superpositions and collapses that generates subjective experience. While this idea is scientifically fascinating, it is important to note it remains a highly speculative and controversial minority view within neuroscience. The warm, wet environment of the brain is considered incredibly hostile to maintaining the fragile quantum coherence we work so hard to preserve in supercooled laboratories. Most neuroscientists explain consciousness through classical, emergent properties of complex neural networks, not quantum effects. Yet, even if the specific quantum brain hypothesis proves unlikely, the very act of proposing it opens a vital interdisciplinary dialogue. It forces both physicists and neuroscientists to sharpen their definitions, to ask what they even mean by terms like information, state, and emergence. This conversation reveals a more robust and fertile common ground in the study of complex systems. Both a human brain and the cosmic web of galaxies are networks of staggering complexity, where simple components obeying local rules give rise to global patterns and behaviors that cannot be predicted from the parts alone. In the brain, billions of neurons firing create thought, memory, and sensation. In the cosmos, trillions of stars and dark matter halos governed by gravity weave the large-scale structure of the universe. The mathematical tools used to describe these networks, from graph theory to information entropy, are becoming a shared language. How does information flow and become integrated in a neural network? How is information encoded and processed in the quantum geometry of space-time? These may sound like different questions, but they stem from the same desire to understand how complexity and order arise from simplicity. This cross-pollination of ideas is more than academic curiosity. It is a necessary strategy. Problems that transcend any single field, like the nature of reality or the origin of consciousness, demand perspectives that transcend any single field. A physicist might see in the brain's neural pathways an analogy for the spin networks of loop quantum gravity. A neuroscientist might look at the holographic principle and see a metaphor for how memories are distributed, not localized, across the brain's cortex. These metaphors are not proofs, but they are catalysts for new kinds of questions. They remind us that the observer is part of the system being observed, and that any complete picture of the cosmos may need to account for the very minds that are attempting to paint it. The collaborative spirit across these disciplines embodies the essence of exploration, recognizing that the deepest truths often lie at the intersections, waiting to be seen by those willing to look from a new angle. Our modern equations may be new, but the questions they ask are ancient. Across millennia and continents, human cultures have woven stories that echo with surprising familiarity to the themes of our quantum cosmic frontier. Consider the widespread myth of the cosmic egg or the formless void. From ancient Egyptian and Chinese traditions to Hindu cosmology, a common narrative describes the universe not as built from pre-existing material, but as emerging from a state of undifferentiated potential, a silent, boundless emptiness that held all possibilities within it. This is a powerful parallel to the physicist's quantum vacuum, that seething non-empty emptiness from which particles flicker into being, and to the singularity, a point of infinite potential from which all space, time, and matter unfolded. Both visions point to a beginning that defies our everyday logic, a transition from a state of no thing into the structured world we know. Similarly, the profound interconnectedness described by quantum entanglement finds a deep resonance in many spiritual and philosophical systems. The Hindu concept of Brahman, an ultimate, indivisible reality underlying all apparent separateness, or the Buddhist idea of dependent origination, where all phenomena arise in interdependence, speak to a universe that is fundamentally woven together. Some indigenous worldviews describe a living, participatory cosmos where observation and relationship actively shape reality, a perspective that intriguingly mirrors the quantum measurement problem and the role of the observer. These are not scientific theories, of course, but they are profound intuitions about the nature of existence, arrived at through contemplation and lived experience rather than particle accelerators. Recognizing these echoes does not validate mythology with science, nor does it diminish the rigor of the scientific method. Instead, it enriches our perspective. It reveals that the drive to understand the fundamental nature of reality, to ask where we come from and how we are connected to the whole, is a timeless, defining human endeavor. Our ancestors used the language of story, symbol, and philosophy to map the mysteries of existence. We use mathematics, telescopes, and quantum circuits. But the destination of the quest feels strangely similar, a yearning to see beyond the veil of appearances to a deeper, unifying truth. This long arc of curiosity connects the shaman gazing at the stars to the physicist analyzing data from the James Webb Space Telescope. It reminds us that science at its best is part of a much larger human story, a continuing conversation about wonder, meaning, and our place within the vast, mysterious whole. The most profound discoveries are meaningless if they remain locked in equations. This is why sharing the journey across the frontier is not a side task. It is a vital part of the exploration itself. Communicating the dizzying complexities of quantum reality and cosmic scale to the public is a monumental challenge, one that demands the careful craft of metaphor and story. We must translate the mathematics of curved space-time into the intuitive arc of a rolling marble on a stretched sheet. We must explain the spookiness of entanglement not with dense jargon, but with a relatable sense of deep, invisible connection. This work of science communication through documentaries, popular books, and channels dedicated to these ideas does more than inform, it builds a bridge. It transforms the alien landscape of superposition and quantum foam into a territory we can all begin to map in our minds. When a complex idea clicks, when someone grasps for the first time that the stars they see are a direct result of quantum jitters from the dawn of time, it fosters more than understanding. It sparks a genuine sense of wonder. This wonder is the engine of future discovery. Planetarium shows that fly us through a simulated cosmic web, or interactive simulations that let us tweak the strength of gravity and watch solar systems fly apart, make us active participants. Citizen science projects invite anyone with a computer to help classify distant galaxies or search for gravitational wave signals in real data, turning abstract cosmology into a hands-on hunt. By making these frontiers accessible, we do not dilute them, we invite everyone in. We inspire the curious student who might one day write the equation that finally unifies the forces. We encourage the philosopher who will help us interpret what that unification means for our place in the cosmos. This broad engagement is also practical. The monumental experiments needed to test these ideas, from space-based gravitational wave observatories to next-generation particle colliders, require significant societal support and funding. When the public feels connected to the quest, when they see it as a shared adventure in understanding reality rather than an obscure academic pursuit, they become stakeholders in the future of knowledge. Ultimately, explaining the universe is how we ensure the search continues, passed like a torch to new minds ready to walk further into the unknown. Theoretical physics is not a finished map, but a living, evolving landscape of ideas. While string theory and loop quantum gravity dominate the conversation, the future of the frontier may well be shaped by paradigms still in their infancy, frameworks so new they challenge our most basic assumptions about how to describe reality. One such radical vision is causal set theory. It proposes a breathtakingly minimalist foundation. Forget smooth, continuous space-time. In this view, reality at its core is nothing but a vast collection of discrete events like grains of sand. These events are not placed in a pre-existing space, they are the space. What gives this collection its structure is not proximity, but a simple, binary relationship, cause and effect. One event either precedes another or it does not. From this sparse network of causal links, the familiar illusions of smooth geometry, distance, and even the flow of time are meant to emerge, like a three-dimensional image forming from a cloud of points. It is a universe built not from stuff, but from the pure logic of connection. From a completely different angle comes the amplituhedron, a geometric object that has stunned particle physicists. For decades, calculating the probabilities of how particles scatter and interact after a collision has involved pages of immensely complex algebra, summing over thousands of Feynman diagrams. The amplituhedron, a multi-dimensional geometric shape, promises to replace all that tangled math with a single, elegant calculation of volume. It suggests that the messy, probabilistic outcomes we observe are actually shadows cast by a deeper, more perfect geometric reality existing in a space without traditional notions of locality or unitarity. This is not just a better calculator, it hints that our entire way of formulating particle physics might be an awkward, roundabout description of a simpler, more beautiful truth. The tools of discovery themselves are also transforming. The immense complexity of these new theories and the colossal datasets from cosmological surveys are beginning to surpass traditional human analysis. This is where machine learning and artificial intelligence are stepping in, not as replacements for theorists, but as powerful collaborators. These algorithms can scour mathematical landscapes for consistent structures we might miss, detect subtle patterns in cosmic microwave data that elude our eyes, or even suggest entirely new, self-consistent equations from first principles. Imagine an artificial intelligence trained on the known laws of physics being asked to propose a bridge between quantum mechanics and general relativity, its digital mind free from our ingrained intuitions about space and time. It might generate 1,000 strange, nonsensical answers, but the one coherent structure it finds could be the clue that leads to a revolution. Perhaps the most fertile cross-pollination is happening with quantum information science. Here, the universe is viewed through the lens of computation and error correction. A groundbreaking idea is that space-time itself, and the gravitational force that shapes it, might emerge from a vast cosmic quantum error-correcting code. In our everyday computers, error-correcting codes protect information by distributing it across many bits, so that if one part is corrupted, the whole message can still be recovered. Some physicists now propose that the holographic principle operates in a similar way. The information about the interior of a region of space is not stored locally within it, but is spread out and entangled across its boundary like a cosmic redundancy. Gravity, in this view, is not a fundamental force, but the thermodynamic force that arises when this quantum information is manipulated. This turns the problem of quantum gravity into a problem of quantum information theory, asking how the universe processes data to create the experience of geometry. The true future of the frontier, however, almost certainly holds surprises we cannot yet conceive. The key to unlocking the quantum gravity puzzle may lie in a mathematical concept not yet invented, or a physical principle so counterintuitive it currently seems like nonsense. History teaches us that every great unification, from Newton's gravity to Maxwell's electromagnetism, required a leap into the unknown, a willingness to let go of comfortable assumptions. Staying open to this radical innovation, to the idea that our most cherished frameworks might be beautiful approximations of something even stranger, is the essential mindset for charting the unknown territories of reality. The next great theorist might be drawing the first lines of that new map right now, in a form we do not yet have the eyes to see. The equations we write and the experiments we build are never isolated from the human world that creates them. As we push toward the edges of understanding, we must also pause to consider the profound responsibilities that accompany such a quest. The pursuit of knowledge at this fundamental frontier, while driven by pure curiosity, is inextricably linked to real-world choices and consequences. One of the most immediate considerations is the allocation of immense resources. Building a next-generation particle collider, launching a space-based gravitational wave observatory, or maintaining a global network of quantum computing labs requires investments that could fund countless other societal needs. This is not a trivial choice. It asks us to weigh the intangible value of understanding the universe against pressing earthly challenges. There is no simple answer, but the conversation itself is vital. It ensures that such monumental projects are undertaken with transparency, clear scientific goals, and a shared sense of purpose, recognizing that the funds represent a collective investment in a future we all hope to understand. The technologies born from this research carry their own weighty implications. A mature, fault-tolerant quantum computer, for instance, represents more than a scientific triumph. It is a tool of immense power that could redefine entire fields. Its ability to crack current encryption standards poses serious questions about global cybersecurity and the protection of personal data. Who will have access to this technology? How do we prevent a new kind of digital divide from emerging between those who can harness quantum advantage and those who cannot? The potential to simulate complex molecules could lead to revolutionary medicines, but it could also accelerate the design of novel materials or compounds with dual uses. Navigating this requires proactive dialogue between scientists, ethicists, policymakers, and the public long before these tools become commonplace, fostering innovation while guiding it toward broadly beneficial outcomes. Beyond technology, the discoveries themselves can ripple through our cultural and philosophical foundations. If a theory of quantum gravity were to definitively suggest we live in a multiverse, or that time is an illusion, or that consciousness plays some role in the fabric of reality, these are not just abstract ideas. They challenge the stories we tell about our origins, our uniqueness, and our place in the cosmos. Such shifts can be disorienting, but they can also be expansive, inviting new forms of meaning and connection. A deeper understanding of cosmic interconnectedness might, for instance, subtly influence how humanity perceives its stewardship of this pale blue dot and any future worlds we may encounter. Engaging with these implications is not a distraction from science, it is an integral part of its maturation. It reminds us that the laboratory and the telescope are extensions of our society, and the knowledge they yield returns to shape that society in turn. By weaving ethical reflection into the scientific process from the start, we affirm that the ultimate goal is not merely to know the universe, but to ensure that our growing wisdom serves the cause of human flourishing and a deeper, more responsible wonder. The true power of this exploration lies not in final answers, but in the questions themselves. Venturing into the space between the quantum and the cosmic is an act of profound personal reflection, a chance to step outside the familiar confines of daily life and let your mind stretch toward the horizon of the possible. It asks you to hold two contradictory truths at once, to accept that a particle can be a wave, that emptiness seethes with creation, and that the solid ground beneath your feet is a magnificent statistical illusion. This intellectual journey, filled with more mysteries than solutions, does not diminish our understanding. It expands our capacity for wonder. It is a direct encounter with the limits of human intuition, and in that encounter we find a deep and necessary humility. We are reminded that the universe was not designed to be immediately comprehensible to a species that evolved to spot predators on a savanna. The rules that govern the fabric of reality are strange, beautiful, and often wildly counterintuitive, revealing a cosmos far more imaginative than anything we could have invented. This realization is not a defeat but a liberation. It frees us from the need for simple, comforting stories and invites us into a richer, more complex narrative about existence. Whether you are a researcher at a lab bench, a student captivated by a textbook, or someone gazing at the night sky with simple curiosity, engaging with these ideas changes you. It rewires your sense of scale, connecting the flutter of a photon in your eye to the gravitational dance of galaxies billions of light years away. That sense of connection fosters a unique kind of awe, a quiet reverence for the intricate, hidden logic that weaves everything together. This awe is the engine of discovery, but it is also a gift to the human spirit. It encourages us to embrace the not knowing, to find comfort in the mystery, and to see our ongoing search not as a gap in knowledge, but as the very space where wonder lives. The frontier is not a distant line on a map. It is the ever-expanding edge of our own curiosity. The most exciting realization is that we all get to stand at that edge, look out into the profound darkness, and ask, what's next? We have journeyed from the shimmering uncertainty of a single electron to the gravitational embrace of entire galaxies, witnessing the places where these two worlds violently and beautifully collide. This is the frontier, a borderland not on any map but woven into the fabric of everything. It is a reminder that our universe is not built on a single, simple principle, but on a dialogue between two profoundly different languages. The quest to translate between them, to find the Rosetta Stone of quantum gravity, is more than the greatest unsolved puzzle in physics. It is an invitation to completely redefine what we mean by reality. Are space and time fundamental, or are they collective dreams of an underlying quantum network? Is our cosmos a unique masterpiece, or one page in an infinite multiversal library? The answers we seek will not just complete a textbook chapter, they will rewrite our story of existence from its very first line. The legendary physicist Richard Feynman once remarked with characteristic wit that he could safely say nobody understands quantum mechanics. That admission is not a failure, but a testament to the depth of the mystery we are privileged to engage with. The frontier endures not as a barrier to our understanding, but as the very space where wonder and discovery live. So let this journey be a starting point. Look at the night sky with new eyes. See in the distant glow of a nebula the echo of quantum fluctuations stretched across eternity. Feel in the solidity of the ground beneath you the astonishing statistical miracle of emergence. How does this perspective reshape your own sense of place within this vast, strange, and interconnected cosmos? If exploring these mysteries lights a spark of curiosity within you, consider joining us for more deep dives into the enigmas of space and time. Share your own thoughts on this quantum cosmic frontier in the comments below. The conversation, like the universe itself, is ever expanding, and the next great insight might just begin with a question from you. The exploration